In this video, we will look at magnetic fields and charges. We will see how a charge in motion behaves in a magnetic field. That is to say, how charge interacts with magnetic field, and how this interaction in the form of magnetic force on a charge can be calculated and quantified. Let's first see how a magnetic field looks like. If you have a standard bar magnet, that is the north pole of the magnet, and that is the south pole of the magnet. Magnetic fields extends from the northern magnetic pole to the southern magnetic pole in loops, like that. So these blue arrows, the curved arrows, are the magnetic fields that belongs to this bar magnet. Now they have directions, so they are vectors. The usual symbol that we use to denote magnetic fields is capital B with an arrow like that because magnetic fields are vectors. The SI unit to quantify the strength of magnetic fields is Tesla, with the abbreviation capital T. Of course, up to this point, we have not said anything about the origin of such magnetic fields or how these magnetic fields are formed. We will more or less address these questions in our upcoming videos. Next, let's see the effect of a magnetic field on a moving charge. Now, let's assume that a positive charge is moving on an XZ plane like that. So this positive charge with the strength Q coulombs has a velocity on an XZ or XZ plane in a following direction, like that. So that is the direction of the velocity, making an angle alpha with respect to the Z-axis. Now let's assume this charge Q is moving in a region where you have uniform magnetic field also pointing along the Z direction. So that is the magnetic field. So this charge Q, positive charge Q, will experience a magnetic force given by the following expression. The force is given, the magnetic force is given by the strength of the charge times the cross product of the velocity vector and the magnetic field vector, like that. From the rule of cross products, we know that the direction of V cross B, namely the right-hand rule, when you curl your right-hand fingers from vector V to vector B, your right-hand thumb will be pointing downward. So that is the direction of this magnetic force. Note also from the cross product rule, the direction of this magnetic force, which is the result of this vector product, will be pointing in a direction perpendicular to the plane containing the magnetic field and the velocity vector. So the direction that is perpendicular to the XZ plane and going in a downward direction is the negative y-axis direction. So if this axis is the positive y-axis, so that axis has to be the minus y-axis, which is the direction of this magnetic force in this example. And we know the magnitude of this magnetic force is quite simply QVB sine alpha, or alpha is the angle between the magnetic field and the velocity vector. Now, if we assume the charge now is a negative charge, then the magnitude is still given by this equation. However, since now this charge has a negative sign, the direction of the magnetic force will be pointing upward. So that is the direction of the magnetic force due to this interaction of this negative charge with this magnetic field. In any case, two important points follow regarding the nature of this magnetic force that acts on a moving charge. Point number one is the charge must be moving. So the charge must have velocity. If the velocity is 0, then there is no magnetic force on that charge, although the charge is situated in a magnetic field. It's simple as that. Point number 2 is the relative direction between the velocity vector and the magnetic field in which the charge is moving. Assume that you have a positive charge and the positive charge is moving in that direction, and the magnetic field in which it is moving is also pointing in the same direction. So that is the magnetic field. Now that would make this angle alpha 0, and that means the magnetic force that acts on this charge is also 0, because sine 0 is 0. Same thing happens if the magnetic field is directed in a direction opposite or anti-parallel to the direction of the velocity vector of that charge. So in this case, the angle is not 0 degrees, but 180 degrees. And since sine 180 degrees is 0, that would make the magnetic force on this charge moving in that way in a magnetic field oriented in that direction to be 0 as well. Let's look at this particular case where you have a positive charge with, let's say, strength Q moving with a velocity v in that direction in a uniform magnetic field. Now when we say uniform magnetic field, the direction and the magnitude does not change. Now the direction of this magnetic field is into the board as represented by such crosses. So the magnetic field is going into the plane of the computer screen. Recall that the direction of the magnetic force follows the simple cross product rule. So using the right hand rule, when you curl your right hand fingers from this direction to the direction into the plane, then your thumb will be pointing in an upward direction. So that is the direction of the magnetic force on this charge at that point. Note, this positive charge already has an initial drift to the right as represented by this velocity vector, and this velocity has a constant magnitude, so the speed is constant. Under the influence of the upward force, what this charge will do, it will gradually go up like that, and it will end up there for the moment. And what happens then? At that point, of course, the velocity vector is heading vertically upward. Now when you make a cross product between a vector that goes up and the vector that goes into the board, you end up with your right hand thumb pointing leftward like that. So when that charge is at that location, the magnetic force is pointing leftward. This will cause the charge to drift leftward like that. Next, what happens when it gets to that location? This velocity vector is leftward like that. Magnetic field is going into the board. At that point, the magnetic force using the cross product rule will be heading downward, vertically downward. So that is the magnetic force on this charge at that location. And this downward force will cause the charge to bend downward like that until it gets to that position where the velocity vector is vertically downward. The cross product between the velocity vector, which is in downward direction, and the magnetic field, which is going into the board, will cause the charge to experience a magnetic force in a rightward direction like that, which will cause the charge to bend rightward and get to the original point. The net result is the charge tracing out a circular orbit with radius r. This is a uniform circular motion. So what is supplying the centripetal force is quite simply the magnetic force, which is QVB. Now the alpha at all the points is 90 degrees. So that is the angle between the velocity vector and the magnetic field at all points is always 90 degrees. Sine 90 is 1, so you end up with QVB. So this V will cancel that V, We end up with an equation V over R equals Q over M times B. This V over R is quite simply the angular speed of this charge as it moves around that uniform circular motion. Since period equals 2 pi over angular speed, we can use this equation to compute the time it takes for this charge to go one complete circle. Substituting this expression in here, we get the period for the motion to be 2 pi m over q times b. Let's look at the following problem. A proton moves through a magnetic field with strength 2 Tesla directed along the positive z-axis as shown by this figure. If the proton's velocity is 2 times 10 to the power of 5 meter per second in the xz plane at an angle 35 degrees to the positive z-axis, what is the magnetic force on the proton? Let the charge of the proton to be that. The magnetic force is given by Q V cross B. So the direction follows the cross product rule. As you scroll from V to B with your right hand fingers, the thumb will be pointing downward. So the direction of this magnetic force is in the direction of minus j hat, which is a unit vector along the negative y-axis. The magnitude can be found by simply multiplying the charge with the speed with the magnetic field times the sine of the angle between the velocity vector and the magnetic field. Multiplying the charge with the field with the magnetic field strength and sine of that alpha, you get following for the answer. 3.67 times 10 to the power minus 14 newtons. So that is the force heading in that direction, and that solves the problem. Problem 2. A positively charged particle with mass of that much kg and strength of that much coulomb with speed of 5 million meter per second moves in a region where uniform magnetic field exists. The motion is depicted below, so it moves in that direction in a semicircular orbit. Find the magnitude and direction of the magnetic field that will cause the particle to follow the semicircular path shown below. And what is the time required for the particle to move from C to D? Note that this charge at this point is starting to deflect rightward, so the force has got to be that way. So that is the magnetic force. The direction of the magnetic force is rightward. So that means, since this is a positive charge, the only way for that to happen is for the magnetic field to come out of the board, as shown by these dots. So the direction of the magnetic field is out of the plane, like that. The magnitude of the magnetic field can be computed from the equation that we have written down a few minutes ago, m over q, velocity over the radius. The mass is 9.11 times 10 to the power minus 31. The speed is 5 million meter per second. The charge strength is 1.609 times 10 to the power minus 19. And the radius is 10 cm. So converted that into meters, 0.1 meter. Note that this entire distance is 20 cm, so that's the diameter, so the radius has got to be half of that, which is 2.83 times 10 to the power minus 4 Tesla. So that is the magnitude, and that is the direction. Next, time the particle takes to complete the semicircle. Now we know omega, the angular frequency, is given by the magnetic field times q over the mass. So for the full period, that is for the charge to go the whole complete circle, will be 2 pi times m over b times q. Since we are interested only in time it takes to go from C to D, namely semicircle, the time for semicircle is half of capital T that we have computed there, which is that. Substituting the value for the mass, the value of magnetic field from here, and the charge, we get 6.28 times 10 to the power minus 8 seconds for the time. And that solves the problem. Thank you for watching.